Hello everyone. Today we will discuss a method for wideband frequency modulation. WFM in analog nonlinear modulation systems known as the Armstrong method. There are two methods for generating FM signals: direct FM and indirect FM. Direct FM modulates the instantaneous frequency of the output signal by using the modulating signal to directly control the parameters of a reactive component. Using a VCO voltage-controlled oscillator, this method can achieve a large frequency deviation, but the frequency stability is poor. An automatic frequency control system is required to stabilize the center frequency, making its implementation relatively complex. Indirect FM, also known as the frequency multiplication method, can achieve wideband FM with lower complexity. In engineering, it is also called the Armstrong method.
Was this method invented by an expert named Armstrong?
Yes, today we will focus on discussing this method. First, let's look at the concept. First, integrate the modulating signal, and then perform phase modulation on the carrier to generate a narrowband FM NBFM signal. This is relatively easy to implement. Then, pass it through an N times frequency multiplier to obtain wideband FM, WFM. This method offers good frequency stability. The drawback is that it requires multiple stages of frequency multiplication and mixing, making the circuit more complex based on the above concept. We draw the block diagram. Let's further examine the implementation principles. Step 1. Generate the narrowband FM signal. From the NBFM formula, it can be seen that the NBFM signal can be considered as composed of a quadrature component, purple circle, and an in-phase component, red circle. Step 2. Frequency multiplication. The purpose of frequency multiplication is to increase the modulation index, thereby achieving wideband FM. A specific implementation method is to use a nonlinear device. Here, we use an ideal squaring device as an example for discussion. First, look at its input-output characteristic. When the input signal is an FM signal, mathematically, frequency multiplication involves squaring the formula, e.g. x becomes x squared. After multiplication, expand using the product to some identities and remove the DC component 1/2a, a fair analysis. After filtering out the DC component, a new FM signal is obtained, whose carrier frequency and phase deviation are both doubled, red circle. Since the phase deviation is doubled, the modulation index is also necessarily doubled. We can conclude that after N times frequency multiplication, using squaring devices for further multiplication, the carrier frequency and modulation index of the FM signal are increased by a factor of N. Let's discuss the issue of frequency multiplication through a typical example in an FM broadcast transmitter. In this example, how many times of frequency multiplication are needed to achieve the final frequency deviation requirement of 75 kHz? According to the formula, N equals final frequency deviation, phase initial maximum deviation equals 75,000 divided 25 equals 3,000 times of multiplication to meet the requirement of a final deviation of 75 kHz. Problem identified. So here is the problem. The frequency multiplier increases the phase deviation, but also raises the carrier frequency. The new carrier frequency after multiplication, NF1, is as high as 600 MHz, which does not meet the requirement of FC equals 88 to 108 MHz.
What should we do then? There must be a solution, right?
let's find a solution together. We need to lower the carrier frequency after multiplication. From our study of linear modulation, we know that linear modulation can achieve spectrum shifting, i.e., moving the signal spectrum to a specified frequency position without changing its structure. Based on this idea, we design a mixer that multiplies the input signal with center frequency Fc by a reference signal with frequency Fr, shifting the original spectrum to positions Fc Fr and Fc plus Fr here. Fc plus Fr is called the sum frequency signal up conversion. Fc reduce Fr is called the difference frequency signal down conversion. Use a bandpass filter to select the desired difference frequency signal, thereby lowering the carrier frequency after multiplication. The specific frequency value can be controlled by Fr. So why do we take the difference signal rather than the sum signal? Think about it. The answer is quite obvious. Here, since we aim to lower the carrier frequency after multiplication, we must choose the difference signal. This method is called the Armstrong method in engineering. Engineering implementation method Armstrong method combines frequency multipliers and mixers. First, use frequency multiplication to obtain a large frequency deviation. Then use mixing to perform down conversion to achieve the specified carrier frequency. First, pass the generated MBFM signal through a first stage frequency multiplier to obtain N1 times multiplication N1F1. Then multiply it with a carrier of frequency Fr and use a bandpass filter to select the down converted signal. The center frequency at this point is Fc equals N1F1Fr. Then pass it through an N2 times multiplier achieving N2 times multiplication. Now Fc equals N2 N1F1Fr. In this way, by setting the value of Fr, we can achieve the given carrier frequency Fc, thus meeting both the frequency multiplication and carrier frequency requirements.
Teacher, I understand. Frequency multipliers and mixers are used together. First, multiply to get a large frequency deviation, then mix to downconvert to get the specified carrier frequency, and then multiply again. Wow, that's so clever and perfect.
Now, let's look at the earlier case. Constructing an FM transmitter using the frequency multiplication method.
I recall the previous requirements were a frequency deviation of 75 kHz and a transmitted carrier center frequency between 88 to 108 MHz. After mixing, the transmitted center frequency is 91.2 MHz. It is indeed achieved.
Of course, we just need to choose Fr appropriately. This section covered the principle and application of the Armstrong method for generating wideband FM. The core problem-solving approach is the combined use of frequency multiplication and mixing. It is also a comprehensive application of previously learned knowledge, linear modulation, spectrum shifting, which is similar to the multi-stage filtering method in single sideband modulation. Through the analysis and problem-solving approach in this section, I hope students can apply it in their future work and studies. Thank you, everyone.